Thank you very much. Hi, everyone. First of all, I would like to say a big thank you to the organizers for giving me the possibility of this presentation. The point what I would like to discuss in this talk is related to the noise in the photometric data series, which series is also called light curves. You can see a simulated light curves here in the bottom left part. This is what we would like to see because then the life will be much, much easier. But actually, as I will show it later, this is not the reality. The reality is quite far from such a beautiful light curve. So the light curve is not constant and not flat between two consecutive transits. So practically, we do not see this. In practice, we see something like that the black points are real measurements of TOI 2046, which is a hot Jupiter detected in the test data. It was published last year with the code what I would like to present here or introduce here. Actually, this star shows not only the transits, but it also shows some kind of quasi-periodic modulations due to stellar spot activity in the first sector. And in the second sector, there is a continuous decrease in the flux, and all of the over the quasi-periodic modulation, probably due to the stellar activity or spot modulation of the star. And all of these things requires cautious pre-filtering of the light curve or a simultaneous fit of the transit model and the noise model, and this can be done in several different ways. Here I did it with wavelets. This is the main topic of the talk. And after I corrected the observed data points for the red noise, and simply I subtracted the red noise component from the light curve and I face folded it, I get the figure on the right, which is practically a textbook example of a nice, normal hot Jupiter transit. I would like to illustrate the problem with another example, which is GG367. This was also detected in the test data a few years ago. The orbital period is just 8 hours, and the transit depth is just over 200 ppm. And the radial velocity amplitude is 80 centimeters per second, practically twice as big as the planet produces in Proxima Centauri B, which was presented by Joao just a few minutes ago. And on the bottom, the top left figure shows the test simple aperture photometric light curve. These are the black points, and the transit model is represented by this green curve. So you can see the very frequent transits, which are much, much smaller than the widths of the original data. And the red curve is the transit model plus the wavelet-based noise model. And after subtracting the red noise component from the observed data, phase folding and binning in the phase space, we can get this beautiful transit light curve on the bottom left diagram. The blue points with the error bars are the binned data points, and the red curve is the fit. And this is a very, very small planet. Actually, in the mass radius diagram, it occupies this region. This diagram was made about 1 year before Joao presented an even smaller planet. So the GG367b has about 0.72 Earth radii and 0.55 Earth masses. Actually, this is the second smallest planet found in the test data until today. The even smaller one is just 3% smaller in radius than this one. So the talk will be about how to reproduce the noise here in the data and how to model it and how to subtract it from the light curves. Because we have a lot of instrumental and astrophysical noise sources. So here I collected just a few examples from the Kepler Q1 light curves. And you can see many effects, which are due to the stellar spot sparsations or even instrumental effects like flux jumps or long-term changes, but also an eclipsing binary can show extra eclipses due to a planet, but then the eclipsing binary eclipse is a disturbing factor for us. So all in these cases, we can, I just skipped this, we can use the wavelets. Actually, there are many other ideas how to play with the noise. For example, you can use some polynomial-based or other moving average pre-filtering of the light curves. But you can use also Gaussian processes, which is powerful, but even the fastest codes can slow down when you have 1 million data points. This will happen in Plato, which will collect about 1 million data points per year in the 25 seconds short cadence mode. But we already have examples from Kepler. For example, Kepler 5 has about 1.2 million photometric points over the 4 years continuous observations. And Spear-Max did apply the GP only on every 1,000 points and interpolated between them to get a photometric light curve solution. And then there is a natural question that what about shorter term variabilities? So I utilized the wavelets, which are described very detailed in the Carter and Wynne 2009 paper, which appeared in the Astrophysical Journal. It needs only 2 parameters, a white noise parameter, which is equal to the white noise in the light curve, and the red noise factor, which just scales the amplitude of the red noise or the correlated noise in these light curves. And it seems to be really fast, even if one uses all points. For Kepler 5b, using all the 1.2 million data points, I received a light curve solution within 6 hours with the wavelet noise model. And actually, my computer in the institute is quite old, almost 6 years old, so time to change, but it really worked also on this old computer. But wavelets has a danger of overfit. Actually, Gaussian processes also have this, so one has to be very cautious. So I applied a penalty function, which is shown in the next slide. So the basic code, TLCM, Transit and Light Curve Modeler code, can fit the light curve and radial velocity curve separately or simultaneously. The stellar radius obtained from Gaia, for example, can be a constraint, but it is not necessary that you use this constraint. Also, log G and effective temperature of the star can be used as a constraint. Several limb darkening laws are included. The gravity darkening effect is also included, and beaming and ellipsoidal and reflection effects via physical description are also included into the code. So what are wavelets? Just very shortly, because we don't have too much time, but for example, this function which is visualized here, the sinus 2x minus sinus x over x, is a wavelet immediately. But there are many different definitions for a wavelet. Different kinds of form of wavelets can be imagined mathematically. And you can create more and more wavelets, which are denoted by psi-mn. And A is just a scaling factor, B is just a shifting parameter, and M and N are integers. And actually, the wavelets work quite similarly to the Fourier transform in some sense that the mathematical formulation is quite similar. So if you have a signal, observed signal xt, then you have to calculate this orthonormal basis, which gives an amplitude for every psi-mn function, which is somehow a periodic function. And in a very similar way to the Fourier series, you can set an ST function, which is practically describes the signals. So how this works in the practice? So I use a condition, an extra condition, because the likelihood of the residual curve is maximized according to this paper. But to the likelihood, I add a penalty function, which is based on the condition that the standard deviation of the final residuals must be equal to the average photometric noise level. So we have to know the average photometric noise level very well. And here you can see just 2 examples where I injected light curves, synthetic light curves, into the Kepler-1 data, and I try to fit them, and I monitored that how precisely I can get back the injected light curve and the parameters which were used for the synthetic light curves. So panels B are the synthetic light curves, panel A are the light curves convolved with the Kepler examples to show jumps and showing spot modulation and whatsoever things. Panels C are the joint model of the transit and the noise model. And then after removing the red noise component from the observations and phase folding, we can have these. And these are two good representation, and also the very small secondary occultations were coming back after the modeling. So if we look at the results, for example, K describes the planet to star radius ratio, and we normalize it, and if it is expressed in percentage, then you can see that how precisely the method works at different signal to noise ratios, also for the A2, which is the geometric albedo of the planet. And yeah, for example, the Plato requirement is plus minus 2%, which is represented here by the dashed lines. And at relatively low signal to noise ratios, we can get this back. So I would like to show you a further example just to further validate the code. So WASP-19 was observed by TESS, and it was also investigated by another team in 2020. So it is a good example to really compare my method to others' method. So the raw light curve, the TESS simple aperture photometry fluxes are on the y-axis here on the top left figure, and time is on the x-axis, and you can see that there is some some long-term variations. There is also a data leak between the two parts of the light curve because the TESS downloaded the data, so we have a data gap here, and the transits are here. On the top right figure, you can see the result of the joint transit model plus phase curve model plus noise model fit. And if we remove the red noise flux, then we can get a very nice transit fit. It is beautiful. And also, if we look at the whole light curve, then the fit suggests that there is a secondary here. And it is quite hard to see that this is really a secondary transit event here or not. So I binned the light curve, and the result of the binning can be seen here. The gray points are the original TESS data points after removing the red noise component from them. And the black points with the error bars are the binned version of the data. And an occultation depth of 445 plus minus 96 ppm was detected here. And since this is not a new result, because this was already observed by Wong et al. In 2020, but this is a good opportunity to compare these results to each other. They used an absolutely different noise treatment, and they found 470 plus 130 minus 110 ppm occultation depth. So I would say that these two ones are quite compatible to each other. Also, the error bars are relatively well. So I would say that the code is validated. So my conclusions and some words about the code availability. So it seems that we found an appropriate regularization function for the wavelets to avoid the overfits. And this approach was tested actually more than 1,500 light curves. And we give the precision one can reach at a given signal to noise ratios in the corresponding publication, which is actually the second one in arXiv. So I found that wavelets can be very useful for noise removal, regardless for its origin. The code, maybe I am the only one who does not publish the code on GitHub. I publish it on my own page, transits.hu. The stable version 96 is there, and the new version will come in the coming days, a beta version 96. It is running under IDEA. The GDR version will come at some point, so there is a free version of IDEA. My institute has some funding to rewrite the code in Python, but when? This is a good question. And actually, the source of the code is also available on this homepage. And the references are given here. And I would like to tell that the organizers of this workshop had a very good idea to organize this meeting, because it is really hard to publish and discuss open source codes or any other kind of codes what we are using from day to day. So thank you very much for this idea and to organize and for the organization of this meeting, and thank you for your attention.
Thank you very much, Szilárd. Is there any question for the speaker? I don't see any question in the room, maybe on Slack. No, I don't have any questions there either. So I saw on your last slide that you plan to move maybe the code from IDL to Python. Is that something you want to do, or it's very hard? It's very big to do.
I am not good in Python. I am coming from the old days, but many colleagues proposed to me to rewrite the code in Python, because many people use Python more than IDL or anything else. And I would not like to do that personally by myself, because it takes a lot of time, and I do not see a good price or pride for it. But our institute has money for that to employ young or young informatic people to do that. If this will come, then it will be rewritten in Python in 1-2 years. If it doesn't work, then it will be never be rewritten in Python. Sorry for that. But Python has the option that it can call IDL objects, so there is a function for that.
Okay. Well, I see one benefit is that Python is free compared to IDL.
Okay. Yeah, but now we have the GDL, which is the GNU version of IDL, which is for free. Yeah.
Okay, okay.